Hello and welcome to the channel Pro Pharma. Today I have come again with the second year semester 3 pharmaceutical organic chemistry syllabus, where we are going to see and start with the basics of reactions of benzene. This is the syllabus where we have covered in our previous videos analytical, synthetic and other evidences. We have seen resonance and we have seen Huckel's rule. Those who really want to see, you can visit the Pro Pharma channel, subscribe and check out all these videos. We are coming to the B, where we are going to talk about the reactions of benzene. Today I'm going to introduce you to a topic called as electrophilic aromatic substitution. When I say electrophilic aromatic substitution, I am talking about an aromatic moiety. We have seen through Huckel's rule who all are aromatic, how can we determine a compound to be an aromatic compound. So now it is important to know what is electrophilic and what is substitution. So let's see what's electrophilic. We are familiar with this diagram. We know who are these two people and what they signify. This is Mr. Beggar, who is electron deficient, and I have Mr. Ambani, who can give electrons to him. So Mr. Beggar, being electron deficient, is an electrophile, a group which attracts or acquires electrons. So a group which have ability to attract or acquire electrons is an electrophile. So electrophilic is electrons loving. What are the examples of electrophiles? So these are the ones with positive charge are electrophiles. Some which do not have positive charge but have electronegative atom which pulls electron towards itself, making it electron deficient, those also act as electrophiles. So these are the few examples like H+, H3O+, CH3+, NO+, then AlCl3+, all these Br2, SO3, NO2+, are the usually used electrophiles for substitution reactions. So when I say electrophilic and aromatic, now we know what is electrophilic, we know what is aromatic. So what exactly is substitution? Substitution, what different example can I give? What does this video signify? Yes, it signifies a replacement of one of the player against the another. And who do not know Messi? Yes. So substitution is one of the atom is replaced by the other, and that is called as substitution. So hence we are going to see something called as electrophilic aromatic substitution reactions. So when I say electrophilic aromatic substitution reactions, let me tell you what exactly it is. Now if I take an example of a benzene ring, okay, when X is H, and it undergoes a nitration reaction in the presence of nitrating mixture HNO3 and H2SO4, I get a nitrobenzene. However, the relative rate of nitration for this reaction is 1. But if I replace this X with electron releasing species, if I replace this X with an electron releasing CH3, then what will happen? The relative rate of nitration increases to 25. So it is 25-fold increase in the rate of reaction due to something called as electron releasing or activating species. Similarly, if I replace this X and H and the X is having an electron withdrawing species, then if I replace that by CF3, F is electronegative atom, it pulls electron towards itself, making C electropositive. Ultimately, C will be vulnerable to pull electrons from the aromatic ring. So you can see here the relative rate of nitration drops to 0.000025. So now you will understand what is the importance of electrophilic aromatic reaction when I am going for any synthetic chemistry reaction. So whenever I want a reaction to increase its rate, I can replace it with electron releasing species when I have that is activation. And if I want to have a retardation of any step, then in the synthesis I can replace it by electrophilic electron withdrawing species, which can lead to deactivation. Okay, let's go ahead. Attachments of substituents. Now it is very important to know that whenever I have a aromatic species, it is not only benzene. They have also substituted benzene. So when I have a substituted benzene, and I have an electrophilic aromatic substitution taking place, one of the hydrogen of benzene would be replaced by the incoming electrophile, which is electron deficient. So either I get a E attached at ortho, attached at meta to green substituent, or at para to green substituent. But in some cases, I get ortho and para as a major product. However, meta is a minor product. So in this case, the substituent is referred to as an ortho-para director. And who are the ones which have major ortho-para products and a very minor meta product are the ones which are activators. OH, NH2, OR, NHR, NR2, O-, OC double bond O, CH3, all these along with these halogens are categorized into ortho-para directors. Okay, so those who give me major ortho-para products on electrophilic aromatic substitution, they are called as ortho-para directors. However, if I have another substituent, a blue colored one, and I am getting meta as a major product on electrophilic aromatic substitution, that is on the attack of E+, then that substituent is said to be a meta director. Who all are meta directors? Meta directors are cyano, aldehyde, acid, ketone, ester, sulfonic acid, CF3, NO2, quaternary ammonium. All these are categorized as meta directors because the attack of the electrophile coming takes place at all the three positions ortho, para, meta, but the major one is nothing but a meta. Okay. So we have seen this in the resonance as well. So these are the activators which are electron releasing species, which are categorized as ortho para directors, whereas these are the meta directors which are electron withdrawing species. A very important table, everybody should have this in mind every time whenever they are going for an electrophilic aromatic substitution reaction or for resonance. So let me now introduce you to electrophilic aromatic substitution reactions. If I take an example of halogenation and I have an unsaturated compound and an aromatic compound and I allow a halogenation for both, a very important thing to notice is the alkenes undergo halogenation, but there is an addition product which is created. However, on the same halogenation of an aromatic moiety, I have my aromatic character as it is and I have no addition but substitution taking place. So a major difference is on halogenation of an unsaturated alkenes or alkynes, I get an addition product and hence all alkenes undergo addition, electrophilic addition reaction, whereas all aromatic species undergo substitution. This is a very important thing to remember. Okay. So the specific reactivity of these aromatic system, why do I not get addition product and why do I only get a substitution product, is just because of the presence of pi electron density above and below the plane. We know the benzene structure very well now. And a very important reason is my aromatic moiety has a drive to regain its own aromatic character. The aromaticity is regained at the last step of electrophilic substitution and hence the aromaticity is maintained, and due to this I do not get any addition product where I will have an unsaturated double bond removed from here and a saturation taking place like it is happening in an alkene, but the aromaticity is restored. I have the double bond as it is, but a substitution of one of the hydrogen is taken up by any of the electrophile. Here it is halogenation, therefore an Br plus is attacking and I have Br attached. So what is the general reaction? General reaction is whenever an electron rich benzene ring, we know all that there are pi electrons roaming around, whenever electron rich benzene ring is attacking an electron poor species or giving electrons to electron deficient species, I get a formation of a carbocation which is a benzonium ion. How is the carbocation formed? These two electrons are coming here, a new bond is formed between carbon and an electrophile, and because this bond is broken, the carbon becomes deficient and I have a positive charge. Again, the second point, due to its ability to regain its aromaticity, these two electrons come in, regain the aromaticity of the structure, and I have a substituted product. The H plus left is goes to any of the base present in the solution and is abstracted. So the first step is a rate determining step, a very slow step of formation of enzonium ion, whereas the last step of deprotonation, that is loss of abstraction of a proton by base and regaining aromaticity, restoring aromaticity, is a very fast step to give me a product, or specifically a substituted product. It is important to note that the benzonium ion is having these resonance structures. It is resonance stabilized intermediate, and the resonance hybrid looks like this. We are now familiar with the resonance. We know how these electrons will come here and give me a double bond here and a positive charge here. These electrons will come here, double bond here and a positive charge here, ultimately giving a resonance hybrid where positive charge can be on any of these carbons. So this is a basic general mechanism of electrophilic aromatic substitution, where first step is RDS and the second step is rapid deprotonation. So this is a 3D view where I have an electron poor species, an electron rich benzene, electrophilized and generated, and there is a transition state where benzonium ion is formed, and then lastly a product is formed where new bond is created between E and electrophile and benzene, and the H plus is lost to the system to get a substituted product. So this is a 3D view of our electrophile generation, formation of transition state, and ultimately substituted product. I hope you have understood it. Thank you for watching this video. Do subscribe Pro Pharma channel, like and share the video. Thank you so much for patient hearing.